All right, let's get straight into it. Today, we're going to pull apart a real national grid question from a GCSE physics paper. My goal is to break it down step by step so you can see exactly how to lock in every single one of those marks.
So, take a look at this. This is the diagram that sets the scene for our question. It's basically the journey your electricity takes all the way from the power station, through these transformers and massive transmission cables, and finally to us, the consumers. This whole setup, that's the national grid. And really getting your head around this diagram is the key to acing the question.
Okay, first up, transformers and transmission. The first part of the question zooms right in on that little box labeled X, the transformer that sits right by the power station. You know, its job is absolutely vital for getting that energy across the country without wasting it all. Right here it is, question 1.1, a classic fill-in-the-blanks. It's asking about the two main jobs of a step-up transformer. So what two words do you think are missing here? Have a think about that relationship between potential difference, voltage, and current.
Okay, did you get them? The words you're looking for are increase and decrease. A step-up transformer is used to increase the potential difference, which then forces the current to decrease. But why? Well, this is the really clever bit. A lower current means way less energy is lost as heat while it's zipping through the cables, which makes the whole grid so much more efficient.
Let's keep moving. Next section, the power loss equation. So now that we've established that we want to keep power loss to a minimum, the exam's going to check if you know the physics equation that actually describes it.
And here we go, question 1.2. It's a multiple choice. They give you 4 options, but only one of them is the right tool for the job. Which one correctly links power, current, and resistance so we can figure out power loss in a cable?
And the correct choice is P equals I squared R. You'll find this on your physics equation sheet, so no need to panic and memorize it. Now you might be wondering, why this one and not P equals IV? Well, it's because this equation directly links power loss to the current and the resistance of the cables. And see that little I squared? That's the secret. It means that even a small drop in current has a massive impact on cutting down power loss.
Okay, equation in hand, let's put it to work. For question 1.3, they give us the power loss and the current. Our job is to calculate the resistance of that cable. This is a 3 marker, so let's make sure we bag every single point.
This is the game plan for getting full marks every single time. Step 1, just write down the equation. P equals I squared R. That's 1 mark. Easy. Step 2, plug in the numbers they gave you. Boom, 2nd mark. Step 3, just rearrange it to get R on its own. That's your 3rd mark right there before you even touch a calculator.
Now punch that into your calculator and you get 400. And please don't forget the units, that's so important. The final answer for resistance is 400 ohms.
Awesome, we're flying through this. Next up, section 3, the efficiency equation. The question now kind of shifts gears, moving away from power loss and onto the bigger picture of the whole system's efficiency. It's another one of those really fundamental ideas in energy transfer.
Now, this next question is a bit of a gift, really. It's just asking you to write down the equation for efficiency. It's a straight-up memory test. So, what's the fundamental equation? You just have to write it out in words.
Okay, here it is, straight from the marks game. Efficiency equals useful energy output divided by total energy input. Simple as that. It's just a way of saying how much of the good stuff did we get out compared to all the stuff we put in. You will see this concept pop up all over the place in physics.
And here's a little insider tip. Mark's schemes are often a bit flexible. As you can see here, if you use the phrase energy transfer instead of energy output/input, that's totally fine too. They're not trying to catch you out on the exact wording. As long as you show the examiner, you get the core idea.
All right, we're on the home stretch now. Let's move on to section 4, nailing the final calculation. We've got our efficiency equation, so what do you think is next? You guessed it, we're going to have to use it.
Here's the setup for the last part of the question. We're told the total energy input is 34.2 gigajoules, and the efficiency is 0.992. Our mission is to figure out the useful energy output, basically how much energy actually makes it to our homes in the end.
And we're going to use that exact same full mark method again. Step 1 is substitution. Pop the numbers you know into the equation you just wrote down. Step 2 is rearrangement, a simple multiplication to get useful energy output all by itself. Showing these 2 steps clearly is absolutely key.
And the final answer is
33.9 gigajoules. And just like that, we have worked through every single part of question 1. That's all 10 marks in the bag. Nice one.
So, what have we really learned here, beyond just the national grid? We've actually learned a method, a way of thinking, that you can apply to pretty much any calculation question in your physics exam.
So remember this 4-step blueprint for success. 1. Start with the correct equation. 2. Show all of your working steps. 3. Substitute your values carefully. And 4. Always state your final answer with the correct units.
You see, when you break it down, even a really complex-looking problem is just a series of simple logical steps. So the real question is, how are you going to take this method forward to boost your own confidence in your next physics exam? Thanks for watching.